Good afternoon, everyone, and for any fellow Americans out there, happy or not so happy 4th of July. I'm Ken. I'm from New York University, Abu Dhabi, pursuing my PhD. So I'm originally more of a computer science or like electrical engineering guy who's pretending to be a soft materials haptics actuator guy in this conference. So at least I've learned a lot of nice soft or materials idea from everyone here. So thank you very much for that. And for today, what I would to talk about is on the characterization of low cost and power efficient UV-Photomechanical MXene Polymer film actuator. Yeah, it's a mouthful. So at least for the first 2 years of my PhD, I was kind of clueless what's out there in the soft material field. So I was experimenting with different stuff. So this is what corresponds to what Professor Ray Jun Lee talked about in Monday plenary meeting on all the stuff that people don't talk about, all the failures, right? So I've worked on soft material memory polymers. I've worked on bulk actuation of photo or thermally actuated mechanical crystals, and as well as for a brief time thermal mechanical muscles. And the issues with all of these technologies was that it's usually slow, or a combination of irreversible, there's hysteresis, expensive to make, and even brittle. So our lab was looking for some novel materials to work with. And luckily, 1 month before the submission deadline for this conference, we did find a nice material, which was MXenes. And basically, it's in theory, 100% photothermal converting materials that we can use for all of the technologies we mentioned above. So what is this MXene material? So just out of curiosity, has anybody heard about it, or by a show of hands, or tried it in their labs before? A few. So it's starting to catch on. It's basically graphene, but with transition metals added aside from some other surface groups. So it's a family of 2D transition metals, and in particular, titanium carbide has been the most well-known example of this family of MXenes due to its photothermal conversion. Right, so how does this work, and how are people using this in the soft, mesoscale actuation community so far? So the heating, the photothermal conversion in the MXene comes from the localized surface plasma effect, which some of the researchers here presented about in some other presentations. And what happens is when you shine a light onto the MXene, the titanium, or any of the metal parts of the MXene resonates, creating this friction-based heating on the film. And what's nice about that is that if you, for example, in particular, this researcher from Hanyang University in Korea, when you put a layer of MXene onto any expanding or contracting materials, such as liquid crystal elastomers, you can quickly induce a heat-induced mechanical bending, let's say through an interfacial stress. Now, the thing that I wondered about this, about the past works, is that all of the films, including this one, has been actuated in the near infrared or far infrared range. But the thing is, if you look at the UV-Vis-IR absorption spectroscopy of, in particular, titanium carbide, the absorption peak is somewhat there, but the higher peak is clearly in the UV region. And I was perplexed why people haven't published any work on UV actuated MXene films. It's not a dangerous range to work with. It's UVA. It's basically like 95% of the energy that's coming from sunlight, and it's maybe causing some sunburns if we go out on the beach for a long time, but otherwise it's pretty harmless light. So we figured we should try it out and see if it works. Right, so instead of liquid crystal elastomers, which we didn't, weren't able to make in, let's say, 1 month before the deadline, but we had a thermosetting photopolymer to use instead for the purpose of this conference. So what this thermosetting photopolymer is composed of are just some polymers. So mainly urethane acrylate, which gives the rigidity and the toughness. So this is used in normal SLA printing, so resin printing in general. And some copolymers, mainly to accelerate the photopolymerization process, or to make the resin a little bit more liquidy, aside from a little bit of photoinitiator, UV pigment, and defoamer, of course. So how we fabricated the film now was to mix the TI3C2 MXene powder, which is basically like this graphite-looking powder over here. We mix this with the thermosetting polymer by hand, and then drop cast this and spread with a film applicator on Teflon or PTFE. And then we just do a quick photo curing in around 10 seconds, and then we peel it with the help of a little bit of alcohol. And we basically complete one film fabrication in like around 10 or 15 minutes, which is pretty fast. So in terms of testing the actuation of the film, we have a simple setup consisting of first the film and most importantly, the actuation source. So the actuation source is a UV flashlight. It's UV Beast, 365 nanometers. The radiation intensity is 5.4 milliwatts per square centimeter, so it's on the lower range, I would say. And then for the measurement, we used thermal camera, distance sensor, and a microscope with a UV filter so that we can show you guys cool videos. So answering the question, how does this film look like in a more zoomed in scale? For example, with this film, if you zoom in with a microscope, the mixture of MXene embedded on the polymer can be clearly seen. It's quite a homogeneous mixture. It's a uniform mixture. And then on the SEM, if you zoom in into more of a 1 micrometer scale, you can see clearly the structure of the titanium carbide MXene. So basically, it's an accordion-like structure that is embedded into a sea of cured polymers. So these sandy-looking grains are the polymers. And we make many samples of these films in different thicknesses and concentrations of MXene volume-wise to see its effect on the temperature of the film, which is important for the actuation and the actuation amount itself. So after a lot of these testing, we have, surprisingly, for a very low amount of MXene concentration, so this is 0.5%, we have what is seen like a peak of actuation, a peak of around 1.2 millimeters, amongst higher concentrations and varying thicknesses. So this is at the thickness of 40 micrometers. And less surprisingly, for the temperature, we have, so compared to temperature for no MXenes and 10% MXene, there is a higher temperature for higher concentration of MXenes with not much effect of the thicknesses. So the optimized from the P point, we got the video. So this is when it's under a UV light and on a UV filter. It was black, that's why it looked green, and then once you turn off the light, it goes down. So it has a bit of curvature because of the peeling process, but aside from that, the temperature also goes from between room temperature to around 37, 38, which is much lower than a lot of the actuations we've seen in the literature. And these can also be seen from the snapshots. So 1.23 millimeter of actuation from the start step. So this is right when the UV light started radiating. And this is at the size of around 1 centimeter. So it's a visible actuation. Now we wanted, because this presentation is about characterization, we wanted to test out mainly the transient response, the cyclability, and the steady state responses. So first, for the transient, we can see, so for the orange shaded part, which is where the UV flashlight is turned on, we can see as that temperature of the film increases, the vertical film displacement goes along with it. Same with the off stage. So once the temperature goes down, there's a bit of probably hysteresis-based lag behind, but the film also goes down. And we managed to do, let's say, 11. On this figure, you see 11 cycles of actuation. So the temperature of the film stays, but as we go through the cycles, you can see gradually the actuation of the vertical film is going down. And to be honest, for this particular optimized film, we couldn't do any more cyclability testing because we accidentally tore it and we were kind of running out of time. But aside from that, we were able to do the steady state test, which also showed a similar kind of slump as we had longer irradiation. So while the UV was on, also the temperature was decreasing, but much more with the decrease in the actuation of the film. And once we turn off the light, they both immediately go down. Now, what to make sense of all of these? So for now, with this particular film, we have a very low MXene concentration, which is nice when it comes to thinking about the cost of making these films, because this 0.5% is very, very low concentration, so it's very nice. And then fabrication was 10 minutes, it's also very nice. And we also have seen that tuning thickness or any geometric tunability can vary the performance of the film. Now, the thing about this film is that we've done more testing since the submission to the conference. There's a lot of variability in the actuation performance of the film. So it's still in the preliminary stage, but we do need to have more quantitative analysis or mass scale testing of the film to really numerically model what is going on, rather it be which parameter is affecting the actuation most. And then we've also done the comparison between past literatures to see that this is, for this particular concentration, a low cost and power efficient film. So in terms of cost, there is no standard metric when it comes to measuring or comparing these films. But at least in terms of cost, we defined it as how much concentration of MXene is used in the film. And then for the power efficiency, we basically defined it as how much bending you can do, keeping in mind of the shape of the shape of the film and how long the bending is. For example, if it's a long film, we took that into account. And the result is that our film goes right around here. So it looks pretty nice as long as we keep the concentration quite low. And the research that we've shown before are somewhere around in this range. So not bad for a preliminary result. And then in terms of the conclusion, we demonstrated that this could be very well low cost and low power efficient UV-Photomechanical MXene-based polymer film actuators. And we have some preliminary ideas for what kind of applications they could be or what kind of further testing we have to do. So one is to have because I'm from a haptics background, a haptics application for pop-up actuators. So for example, people have already, let's see if I'm doing it one more time. So just enough time. So in haptics, people have, back 10 years ago, made this metal surfaces that can dynamically change surfaces for various uses. But what you don't see here is that there's like a very long, bulky electromechanical system below that makes this possible. So if we use a film actuator like this, what we have to do is to put light and then actuate a very thin film surface. And this is also demonstrated in a more elaborate case by Professor Degassi, who is here in our audience. Thank you for coming. So right now, we've only demonstrated a rectangular piece of film, but of course, if we incise the film into elaborate kirigami or origami folded shapes, we can achieve a more programmed actuation that is similar to this one. And of course, the fabrication technique can be made a lot better. So right now we used a commercial polymer, but we could, based on what I've learned from the conference this week, go into much better materials, for example, LC, PDMS, hydrogels, PNEPAM, glass, and of course we will do more testing and characterization. So that concludes my presentation, and thank you for listening.
Thank you. Okay, so probably have time for maybe 1 or 2 questions. Yes.
Thank you. Thank you very much for your presentation. Maybe I missed the beginning of the talk, so I'm wondering what is the actuation process here? I mean, what is the mechanism? Is it thermal expansion?
Yes. So from light to heat to mechanical. So MXene is heated by light, and the heat from the MXene goes through the film, quite uniform thermal
So you
distribution.
have an active layer and a passive layer, right?
Yes. So we mixed the polymer and MXene together. It's just powder and polymer mixed together. So it's actually just a single layer, which is interesting because it still made a bilayer-like bending for some reason, which is
So your actuator composed of only one layer.
only one layer, which is weird, but that's what we saw on video in some cases. Of course, if we also tried with bilayers in the recent few weeks, and they have much more reliable performance. It doesn't vary as much as this one. But
Could it be due to like I don't know, dissipation of MXene layers in the bottom of the layer, so you don't have a homogeneous dispersion across your cross section? Because if this is fully uniformly dispersed, then it doesn't make sense to bend.
Of course.
It should
So
expand in one like planary.
yes. So I showed a quick SEM image of the MXene before. Let's see. Let me go back here. So it is fairly uniform, but not perfect, of course. So there is a little bit of clumps.
That one is maybe from the top view.
Yes.
I'm talking about the cross section.
The cross section, yes.
So if for example the MXene particles are all aggregated on the bottom of cross sections, then it is not homogeneous, and then it makes sense to bend.
Yes.
But if it is across the cross section, if they are homogeneously dispersed,
Yes.
then
True. So that could also be the case. So we didn't have the chance to make a cross section image yet to see what's going on, but it could be the fact that yes, while during the fabrication, it was only 10 minutes long, but MXene could have condensed on the bottom, like because these films do have directionality. If I flip the film, it does still actuate in the same direction, which is interesting. So that could be why. And the other reason could be, I think I blanked out, but we can discuss this more later.
Exactly.
Yes.
I think it's more like electrical charges also.
Yes. The other thing was in the peeling process, because we manually peeled this, so there could be, for example, when you curl a paper, I mean, you use a scissor and you put it on you put the paper along the edge of the blade at 90 degrees, then there's a curl. Similar thing could be happening when we peel it, so that could be pre-stressing the film, which we try to minimize it, but still, it's there. Yes.
Thank you, Ken. Thank you.
Thank you very
So
much.
it's time